So in this video, I'm going to be solving problem 2.26 as it appears in Griffiths Introduction to Quantum Mechanics 3rd edition. Now, it is important to state that in this video, I'm going to be using a brute force method because there is a clever trick that you can use. In fact, it is to exploit the evenness of this potential, and you can use that to find the solution to this problem in a much easier way. And in order to do that, you have to use the trick that I showed in my previous video. If you have not seen it, you should definitely see it. And I did want to, however, show you how you could do this problem if you didn't know the trick, if this may appeared on an exam or something and you couldn't think of this trick. I just want to show you how you could solve it like this. In the next video, I'm going to solve this same problem, but that time I will use the trick and I will show you how in fact it is much easier once you do use it. So for now, let's just focus on this brute force approach. So this problem tells us to consider this double delta function potential, which you can see right there, where alpha and a are positive constants. First, we are asked to sketch the potential. So let's just sketch it quickly. Let's say two axes. This is going to be y-axis that we can just call v of x because of the potential, and this is going to be x. So here we have two potential wells, right? We have one located at minus a, and one is going to be located at a. So let's just sketch that real quick. This is going to be at minus a, this is 0, and our a is going to be here. This should be the same distance, but it's just a sketch. So this is what this is going to look like. Now, you can see from this that there is symmetry in this problem, right? They are both at the same distance from the origin, and that's why actually you can use that evenness trick that we'll use in the next video. So for now, however, we will pretend that we don't know about it and just continue brute forcing our way through this. So this is a sketch. So far, so good. Now let us go to part B of this problem, where we are asked how many bound states this possesses. So basically, we need to determine the energy of these as we did in the case of just one delta well. And what we are going to find that in this case, it's not quite as simple as determining just the energy. That's why we are asked to find how many bound states they are, because it's not as simple. But the procedure is the same. We have to go in that same direction. So let me just copy this drawing actually, because it will come in handy. So now what we want to do, the procedure, as I said, is basically the same as what we have done before. This is just a brute force method. There's nothing new here. All we're going to do is use exactly what we have done previously, but now to this problem where there is another delta potential. So let us solve the Schrödinger equation for this. Now notice there are three regions of interest. One region of interest is going to be to the left of this first potential. That's going to be region number 1, and there's going to be a wave function psi1 there. There's going to be a second region with a wave function psi2, that's going to be in here. And finally, there will be a third region, psi3, to the right of the second delta potential. So there are three regions of interest, so we are going to need to solve the Schrödinger equation for all of those three. However, unfortunately, I said unfortunately, by the way, so fortunately, they are all, the potential is 0 in those regions, so the solution will be the same for all, but we have to take different constants of normalization, right? So let us solve the Schrödinger equation. So it's just going to be minus h bar squared divided by 2m psi prime, right? Double derivative with respect to x, plus the potential times psi, but the potential that is just 0 in these regions. So this is going to be equal to the energy times psi. Now remember, we are being asked to find the bound states. That means the energy less than 0. So with that in mind, let us now, as usual, solve this d squared psi dx squared. Remember, these two things are the same, and this is going to be then equal to minus 2me h bar squared psi. This is standard procedure here. And now we want to define some constant for this. Since the energy is negative, we can't just define k as the square root of 2me divided by h bar squared, because this is negative and we don't want to take the square root of something that is negative here. So let us include this minus sign inside. So this is basically saying that k squared is going to be minus 2me divided by h bar squared, right? We have done this many times before. So when we do that, we're just going to find that d squared psi dx squared is going to be equal to k squared psi, which is the same as to say d squared psi dx squared minus k squared psi equals 0. And this is something that we have solved many times in the past. I will just go through this very quickly, and if you are not sure how to solve this, then by all means go back a few videos in this course to make sure that you check it out, because it's really important. So we can just factor this as the derivative operator plus k, derivative operator minus k, and this times psi equals 0. And from these two differential equations, we're going to get two solutions. So the solutions are going to be some constant a times e to the kx plus some constant b e to the minus kx. So this is the form of our solutions in these regions where the potential is 0. So let us now name them. So for region number 1, this is going to be the solution. For region number 2, it's going to be c e to the kx plus d e to the minus kx. And in region 3, this is going to be e times e to the kx plus f e to the minus kx. But as I said, in all regions, will have the same form. So just it's the same solution, but with different constants. Now we have to make sure that our solutions are normalizable. That means this region right here is where x is negative. So when x goes to minus infinity, we need this to be normalizable. It has to go to 0. So that means that this term right here cannot be allowed. This is not a physically acceptable solution, because when x goes to minus infinity, this goes to infinity and the integral will not converge. So that is not good. And for the same reason here in the third region, which is where x is positive outside of these two deltas, this term will also go to infinity as x goes to infinity. So we also have to take it to be 0. So our actual wave function then will be in this form, which you could obviously also write as a general form. So psi will be a e to the kx when x is less than minus a, well actually less or equal because of it has to be continuous. Then it's going to be c e kx plus de minus kx when x is greater or equal than a. Whoops, sorry. Okay, I made a small oopsie there. Okay, so x has to be greater or equal than minus a and smaller or equal than a. And finally, it's going to be fe minus kx when x is greater or equal than a. So that's our wave function here. And now we have to try to think back, like pause the video and think, what did we do in the case for just one delta potential? We also had these two regions. What did we do back then? And the answer is we have to now apply the boundary conditions. So there's two boundary conditions, as we have seen many different times. First, we need the wave function to be continuous at each potential, and we need to take into consideration the discontinuity of the derivative. Okay, so let's now begin seeing what happens. Let me just copy this, and let's now take a look at those conditions and see where they lead us. Can I make this smaller by any chance? I don't think so right now. Okay, never mind. So let's begin then by taking a look at the first condition, the wave function, which is basically going to be this one right here. So let's just call it psi1 so that it's clear, evaluated at x equals minus a. So let's just write it as minus a, I guess, so that it's less there's less things written down. This has to be equal to psi2 evaluated at minus a. So let us now just replace this. So we get a e to the minus ka has to be equal to c e to the minus ka plus d e to the ka. So that comes from this first condition. Let me maybe push it to the side a little bit. This is our first condition. Let's label the equation equation 1. Now let us take a look at the second condition for continuity of the wave function. So that means that our wave function, that is, it has to be continuous throughout this second delta potential that is located at x equals a. So the wave function to the left, which is psi2, evaluated at a, has to be equal to the wave function to the right, which is going to be psi3, evaluated at a. So this will now lead us to fe to the minus ka. I wrote it the other way around, but this is the third, right? This is going to be equal to ceka plus de minus ka. So this is going to be the second equation that we get from these conditions. Now we have to take a look at the conditions of the discontinuity that happens because of this infinite potential that we have. Now we have done many times, the way you get this is that this discontinuity will come from the integrating the Schrödinger equation. However, I've done this twice in the past 2 videos that I made on this topic, so if you don't know how this goes, then pause the video and go check it out, and then you come back, because it's very important, and it is not all that short, so I'm just gonna skip it this time. So what we know from that is that the derivative, let's now take a look at what happens at x equals minus a. So the derivative of the second wave function, so in the second region, with respect to x, evaluated at minus a, minus the derivative of the first one, evaluated at minus a, has to be equal to minus 2m alpha divided by h bar squared times psi evaluated at minus a. So this is our condition. As you recall, this is exactly the same as we saw before. As I said, if you don't know where this came from, it's really important that you go back a few videos when I discuss the problems with these delta functions, because it's important that you know where it comes from. So now let's take these derivatives. So psi2 is cekx plus de minus kx. So when we take that, we are going to see that a k is going to come down and this plus will be a minus. Okay, so let's now write this. So this thing right here will be k times c e to the minus ka. This minus, right, it's because we're evaluating a minus a. This was positive, now it's negative. Then it's going to be minus d e to the ka. This used to be negative, that's why there's a minus sign down here. Now it's positive because of that. I hope you can't hear my dog too loudly. And then we have minus the derivative of this first function. What is that? It's ka e to the kx, but we have to evaluate this as minus a. So it's just going to be minus ka e to the minus ka. And this whole thing has to be equal to minus 2m alpha divided by h bar squared times psi of minus a. But what is that? That is just going to be a times e to the minus ka. Okay, so this is the equation that comes from this third condition. However, we can't simplify this further. We can divide by k, right, because we have a k here and here, so we can write it down here when we divide. And we can also take this a to the right hand side and factor out. So what we're going to be left with is that, now I like to write this term to the left, so I'm going to do that, but it really doesn't matter, but that's just the way I like to write my equations. So I get a e to the minus ka. This will have, now this is going to be factoring because we have an a here and here, right? So we are factoring, so this will be just minus 1, but it goes to the right side, so it's going to be 1. So we get 1 minus this 2m alpha divided by h bar squared k. And now this has to be equal to c e to the minus ka minus d e ka. So this is going to be our equation number 3. So let me now get rid of this. We have already used it, and I don't want to lose sight of this so that we can compare it. Okay, so that's going to be from this first condition. Now let us go now to the second border condition that we have to apply here. So the discontinuity on the delta potential that is located not at minus a, but at a. So in that case, it's going to be d psi 3 dx evaluated at a minus d psi 2 dx evaluated at a. This will have to be equal to minus 2m alpha h bar squared psi evaluated at a. Now let us replace each one of these things by its actual value. So what happens when we take the derivative of this third wave function? F e to the minus ka, so we get a minus k in front, and this will be f e to the minus ka. So this will be minus k f e to the minus ka, and now we have to subtract this right here, which is the derivative of this second one evaluated at a. Now we did this derivative just a few moments ago, so it's this right here. We're going to get a k that comes outside. It's going to be minus k, and then we have c e to the ka minus d e to the minus ka. Let me just make sure that it's right. We get this minus sign here. Did I write the k down twice here? No. Okay, that's great. So now we can just let this minus inside. So let me get rid of this parentheses. Actually, no, the parentheses is fine. I'm just going to leave the k outside, but the minus sign goes in. So I had a minus sign. Wait, okay. Yeah, this right here is minus, and this right here is plus. That's the way it goes. So we get de minus ka minus ce ka. So just as, I almost forgot, we still need to write something for this. So the easiest thing here is just to write this as f e to the minus ka, right? Because we could either take this part or this, but obviously this second one is just cleaner overall, so just let's go for that. Okay, so now we can, just as we did in this previous case, write this a little bit cleaner. So let us add this term to the right hand side. I'll just put it there, and also divide by k. So we can divide by k and write it down here. And also I like to write this positive term first. So let's just write it as we did here. So this part, I will write it to the right hand side. So we get f times a minus ka factor of 1 minus 2m alpha divided by h squared k. This will have to be equal to de to the minus ka minus ce to the ka. Okay, so this is going to be our fourth equation, our fourth condition. So as before, let me just erase this. Okay, so now we have our 4 equations. Let me just go to the next page so that we can see all 4 equations at the same time. Where are equations 1 and 2? Here they are. Well, I'm going to have to do a little bit of cleaning up, but so this right here is not something I wanted to bring, and I will also try to write them a little bit closer together. This right there. All right. So now we need to solve this system of equations, which will be somewhat annoying, but well, just take a deep breath, and now you can just pause the video if you want, go ahead with the algebra, and we have to just choose our favorite method to solve these equations. What you could do is to see, well, equation 3 and 1 correspond to the same boundary condition, and that's why they are relatively similar, and the same goes for equations 4 and 2. In fact, if we take a look at this, and we have this CE to the minus KA plus DEKA, it's basically the same, but we have this minus sign down here. So actually, if we were to add these two equations, so 3 plus 1, equation 3 plus 1, this D would cancel out. And that seems like progress. So let's go ahead and do that. So if we add these, and that's why I also like to write these A's in the same part, because it's easier to see when something cancels out. We have AE to the minus KA times 1, and here AE minus KA times 1. So what we will have on the left hand side is AE to the minus KA times 2, right? One from here, minus 2 M alpha H bar squared K equal, now we have 2 times CE to the minus KA, and this D cancels out. Now these two, we can just divide by 2 because there's a 2 everywhere, so that way this looks a little bit better. And there we go. Now we can also multiply through by e to the KA, so that this goes away, and so does this. And now, lo and behold, we actually found an expression for C, which is kind of nice considering this was looking, well, not so nice. So I'm going to write this in the next page so that we can use it later. This is going to be our equation number 5. So let us now go back and do the same thing, but this time with equations 4 and 2. Let's take a look at them. So the left hand side looks pretty similar, except with F instead of A, and the right hand side is also quite similar. So if we add them up, C, the C part will cancel out. So that also seems like progress, so let's go for that. So let's add them. So we get equation 4 plus equation 2. So on the left hand side, we're going to get F e to the minus KA times 2 minus 2m alpha H bar squared K. This will be equal to, now the C's cancel out, so we just get 2DE to the minus KA. So as before, there's a few things we can do here. The 2's will cancel out, the exponentials will cancel out. So we are going to be left with something that is a lot simpler, which is going to be that F times 1 minus m alpha divided by H squared K is going to be equal to D. So let's now take this to the next slide as well. Write it right next to this other relationship, and this will be equation number 6. So now we have expressions for C and D. Now what we can do is write them into equations 1 and equation 2. And that way we are going to have a relation between all of our constants. So that's what we want. So let us then do that. So let us put equation 5 and 6 into equation 1. So first, what is equation 1? Let me just copy it so that we can actually work with that. So when we do that, oh, there we go. So let us now put 5 and 6 into 1. So, well, this A part will stay the same, right? This is 5 and 6 into 1. AE minus KA will stay the same. Then we have CE to the minus KA. What is C? C is this thing right here. So it's going to be A e to the minus KA times 1 minus m alpha H bar squared K. And then we have plus D, but D is this right here. So it's going to be F times e to the, to the positive KA to the KA times 1 minus m alpha H bar squared K. So now there's a few things we can notice. This term will cancel out this right here. When we multiply through, it's the same thing. You can just subtract from both sides. So after we do that, we have this minus sign here. So let us just add this to the left hand side where there is currently a 0. So what we get is a e to the minus ka times m alpha h bar squared k. This is going to be equal to f e to the ka times 1 minus m alpha h bar squared k. So what we can do here is we can divide by this term, and we can also multiply by e to the ka, so that we get rid of all that is in this right side. So this will go away, and on the right side we are going to get e to the 2ka. And also when we divide by this, it's the same as multiplying by h squared k divided by m alpha. So when we do that, this term right here will be h squared k divided by m alpha, and this other part will just be minus 1. So this also goes away. So now we can actually see that a is going to be equal. Okay, let's try and select this somehow without moving everything. Let me just delete that. Okay, so a will be this right there. Okay, so let me now select this, put it on the next slide, and this will be equation number 7. Now we are going to do the exact same thing, but for equation number 2. So we're going to put equations 5 and 6 into equation number 2. So what is equation number 2? Let me just go back a few slides. There we go. It's this right there. And where was I? Here. Okay, so now let's put c and d into this. So it's going to be f e to the minus ka. So c is this right there. It's going to be a e to the ka 1 minus m alpha h bar squared k. And then we have plus d, which is this part right here. So f e to the minus ka. Remember, these exponentials that I'm writing here are the ones that are already here, right? Because there's no exponential in here. That's going to be 1 minus m alpha h bar squared k. Okay, so as before, we can do a few simplifications. So this part will cancel out this f right here, and there's also this minus sign, so we can now add this to the left hand side as we did previously. So in this case, we're going to get that f e to the minus ka times m alpha h bar squared k is going to be equal to a e to the ka 1 minus m alpha h bar squared k. So this is actually looking pretty similar to what we had before. So now we can just multiply by e to the ka and multiply by the inverse of this. So that will isolate our f. So now we're going to get in this exponential add 2. And here, instead of 1 minus m alpha divided by h bar k, we are going to get h bar squared k divided by m alpha minus 1. I do not want to select that parentheses. Okay, so let's just put that there. And this is the result that we want now. Let us copy it and paste it into the next slide. This will be equation number 8. So now notice that these look pretty similar. In fact, let us divide this first equation by f, so that we get that this is just a divided by f. And now let us divide equation 8 by a, so that this is f divided by a. And now, as you can see, a divided by f is going to be the same as f divided by a. Okay. So what does this mean? So basically this says that a squared is going to be the same as f squared. Now this means that there are two possibilities. Either a is equal to f or a is equal to minus f, right? These are the two possibilities. So there are two distinct cases here that, in fact, we shouldn't really be talking about this because this is a brute force method, but this actually is what makes a difference between even and odd cases. In fact, this right here will give us the even solutions, and this right here will give us the odd solutions. But for now, we don't really know anything about that, so let's just pretend that we don't know. So let us actually now just take any of these relationships, because as we said, they are quite similar. Once we have done this, we have taken A to be either F or minus F. And let's say, okay, let's go for the case A equals F. So let's solve this when A equals F. That means that this will be just 1. Now, remember, we want to find the energy levels. That's the whole reason we're doing this. The energy is hiding inside K. So if we solve this equation right here, we will know what the energy levels are for this problem. Now, unfortunately, that is not an easy task to do, because how do you solve this problem, this equation? This equation is really hard to solve. So what is usually done here is that we are going to try to solve this graphically. So let us now divide by this exponential so that we get to the left hand side e to the minus 2ka, and this has to be equal to h bar squared k divided by m alpha minus 1. So this is the equation that tells us the energy levels, and this is also why the problem didn't ask us to determine the energies of these the bound states. It only told us, okay, how many bound states are there? Because solving this, as I said, is really not easy. You have to use some sort of graphic or numerical method, and you also need a value for alpha. In the original problem, I did edit this problem a little bit, but if you are giving some value for alpha, you can then go ahead and do some numerical calculation or graphical. So how do we solve this? Well, this is a function of k and this is a function of k. So what we can do is make just a graph, right, of these functions of x and in terms of x here. So this is just an exponential. If k is, sorry, I didn't mean x, I want to say k here. Sorry, we have to graph this for k. This is f of k and this is k. So when k is 0, oh, actually k can't really be 0 because k is determined by the energy, and the energy can't really be 0. But if k goes really close to 0, then this exponential will get really close to 1. So it's going to start somewhere over here. And then, well, it's a decaying exponential, so it's just going to do something like that. Okay, that's good. What happens to this right here? Now, this is just a straight line with some constant multiplying it. If k is really close to 0, this will be somewhere around minus 1. Well, this is not very symmetrical, but we're just sketching. We just want to see how many solutions there are. And this is just a straight line going up. So this is just going to go up like that. It has a positive, this is positive, so it's going to be going up. And we can see there's going to be precisely one solution. So that is actually the answer here. These solutions for when a is equal to f is just one solution. And just so that we, well, actually we're going to do that later when we sketch it, so I'm going to leave it for later, sorry. So this is our first part. You can even see at which k this happens, because that would mean you just have to see when h bar squared k divided by m alpha minus 1 is equal to 0, so you can easily find at which k this happens. So that is the case for a equals f. Now let us go to the case where a is equal to minus f. So once again, let us take one of these equations. It doesn't matter which one, you are going to get the same result. So now instead of this being 1, let's write it minus 1. So similarly as before, let us divide by this, so we get minus e to the minus 2ka. This has to be equal to h bar squared k m alpha minus 1. And the easiest way to solve this is just to multiply through by minus 1, so that we get 1 minus this thing right here, right? That's going to, whoops, I meant to move it. There we go. Okay, So now let's graph this similarly as we did before. So once again, a graph in terms of these functions of k as k changes. So this exponential begins at 1 and then decays. And then we have this part right here, which is also a straight line, but this time it's different. When k is very close to 0, this also begins at 1. But then depending on the value of k, of alpha, this slope will be different. So it is possible here that if the slope is very small, it is possible that there is no solution because the straight line is just going to be somewhere around here. It might even be just a horizontal line. And in that case, there would be no solution. So that means that whatever this case of a equals minus f means, it's the odd solutions, but don't tell anyone. But so whatever that means, it will not always have a solution. And in fact, depending on the value of the slope, you can have one or even two solutions, depending how this intersects, how this line going down is going to be intersecting. Right? There can be several different possibilities here. So those are our bound states, and that's what is asked of us in this second part. If we knew the values of alpha, we could determine the energy levels using some sort of numerical or graphical method, but usually most courses do focus on this part. So if it's maybe more of a mathematical course, it is possible that they want you to do something there, but this is usually at least where the physical part, this is what matters for us physicists most. Obviously you want to know the result, but when you're teaching, this is fine. Okay, so finally, we now want to sketch the wave functions. So in order to do that, remember we have two cases. Case 1, a equals f, and case 2, a equals minus f. So we know about the relationship between a and f. We don't really know much about c and d. So let us go back a step and see if a and f are equal, then we can see c and d are also equal. And if a is equal minus f, then c is going to be, or the other way around, d is just going to be minus c. So we can now write our wave function. So let me just write this. C is equal to d here, and here c is equal to minus d, or d is equal to minus c. It's the same thing. So in this first case, we get that our wave function is going to be, let me just copy it. Actually, I already did this before, so I'm just going to copy this. So I'm going to delete this. Oops. Okay. Well, it is somewhat larger than I want it to be, but it's fine. So now f is equal to a, so let me just write it here, and c is equal to d. So we can just factor this out. Okay, so what does this look like? So let me just put the graph down over here. So we are going to be graphing psi as a function of x. And remember, we are going to have, here is going to be at minus a, one of our deltas, and at a, there's going to be another one of our deltas. So first, we're going to have this exponential part that's going to be decaying for the, remember, this is region number 1, inside here is region number 2, and to the right here is region number 3. So in this first region, it's going to be decaying ever after this delta potential. And the same thing is going to happen after the second delta potential. And then here in the middle, we have this that, well, here you can apply to see exactly what happens. You can apply this derivative test. There's a few things you can do, but you can also see that this is going to be an even function that is going to be falling off as it goes to 0. So it's going as x goes to 0. So it's going to be something. Oh my god, this is not looking as good as I wanted it to, but let's see. I'm going to try and make this look a little bit better. Should be something like that. Well, it doesn't look symmetrical. It's supposed to be symmetrical, but well, let's see if I can make it a little bit smoother, but well, good enough. So this is going to be basically exponentially decaying in this first region, then it's going to be decay until 0, then it grows again, or if you look at it coming from this side, it's decaying towards 0, and then it continues to decay into positive infinity, right? Something like that. So that is it, and as you can see, this is an even solution, right? This is symmetrical. This is an even solution. But as I said, that's something that we really didn't quite know just yet. We are not using the trick. We will do that in the next video, but it's really, really useful to think of it in those terms. So this is our sketch number 1. Now let us actually, I'm going to go pick our solutions here again. And now let us do the same thing, but for the second case. So this time a is equal to minus f. So this time here, well, obviously here you could either take a equals minus f or f equals minus a. Now there are slight differences to the wave function when you do that, but in principle it's the same. So here we're going to get, instead of d, this is just going to be minus c, so we can just factor it out. So this is going to be the wave functions for the second case, which, as I spoiled, is the case of these odd functions. So let's now sketch this quickly. So in this case, actually that did not look very vertical. So okay, that's a bit better. So in this case, once again, we're going to have these two delta potentials at minus a and a, our zeros here. This is region number 2, region 1, region 3, x, and our psi. So now what we are going to get is that we have this decaying part in the first region as before, but now this part is odd. Once again, you can use whatever tricks or methods you want to use in order to sketch this, but as you can see, this is now going to be decaying to 0, and it's going to continue to decay up until some point down here at a, and then it's going to do this, right? So as you can see, this is indeed odd. It's what you would expect, since it's basically this reflection with some straight line here. So these are the sketches of the wave functions, and this is how you solve this problem just by using brute force, by not thinking about the potential at all. So I think it's really good to do this at least once, because it lets you better appreciate the tricks that we're using when you solve these problems in quantum mechanics, but it's not really something that you want to be using in your everyday life, because it is quite annoying. So in the next video, I will be solving this exact same problem, but this time, or that time, I will use the trick that we saw in the previous video, so make sure to watch that before going to the next one, and well, we'll see that it's a lot easier. So I will see you then.